back to class number 1, and we're going to go into chapter 11 of Beer Johnston and have these fundamental kinematic relationships and see how we can use them to describe the motion right here. So we start out with the average velocity, which is something you probably already intuitively know, that we have the average AVG velocity. It's just the change in position over the change in time, right? So yeah, so you look at what the clock says when you leave for a trip, and then when you get to the end, you look what the clock is and you see what the odometer is. You see the difference between those two things, and you're able to figure out what your average velocity was. So you say T2 minus T1. Well, you could do the same thing with the acceleration, right? Now, the instantaneous velocity is what the speedometer says that you're doing, right? So if I skip down to here, if I just say the velocity is going to be dx dt, right? So we take small increments instead of taking these large increments over time, because sometimes you're maybe going to pass somebody, or you're behind a slow truck, or what have you, right? Maybe there's a traffic jam. So here is just what average happens over here. But if you take a look at your speedometer, you're actually making these increments very small time increment, very small distance increment, and you can tell what this is going to be. Now for the acceleration, you could do the same thing. Maybe if you take a look at the speedometer, right, and you press on the gas pedal, you can find out when after setting your stopwatch or something, and you could say here's what my average acceleration was going to be, right? So that's just the difference between the velocity at one time and another time, and then that delta t, that change in time that it takes for you to change those velocities. Now, we most of the time are looking for the instantaneous velocity and the instantaneous acceleration. What we'll often do for this derivative right here, we might make a little shorthand and put a dot on top of it. That just means that we've taken the time derivative of the thing. So if we take a look at acceleration, we have dv dt is the instantaneous acceleration, right? And we could write that as v dot, but we don't often. We'll say x double dot, right? The second derivative of position with respect to time, which we want to remember there is always get to this. So where to put those the squares? There you go, right there. All right, the second derivative of position with respect to time. Now there's another one here that's we can now, instead of acceleration as a function of time, we can also have acceleration as a function of position. And how do we do that? Well, we can write out this dx dt. We could instead write it as dt is equal to dx over v, right? Well, we just multiply that over on this side and then divide out through there. So if we substitute this into a equals dv dt right there, right? We'll substitute this into that. We could end up with the acceleration is equal to the velocity times dv dx, right? So these things flip-flop right here. So we have velocity here. So here is another kinematic relationship. So here's like the basic kinematic relationships right there, all written out for you. And what really helps, I think, with looking at these, just to try as a concept of the thing, is to graph the thing out. So you'll see I've graphed out, here's position as a function of time, right? So this thing, whatever it is, it moves like in a way that you could say is sinusoidal, right? Well, just remember that a cosine is a sine that's just been shifted over right here, and this has been shifted over. But you can see it goes up and down and up and down, and here's like where 0 is right there, right? So I think I got that right. Yeah, somewhere in there. I should have included 0, I think, in my graph. But these derivatives, what we can think of here is, remember that when this thing crosses 0 right here, or when this thing peaks, that's going to be where that's a 0. We could also say that when the position right here, we have a maximum thing right here, we have a slope right there, right, of 0, right? Because remember, we're taking this right here is a slope of position with respect to time. Here is position with respect to time. So if we have something that's flat right here, this is always the slope. So like we'd even say, like right there, here is the velocity right there. And you can see that that's kind of like where it's going to be a maximum, right? That's where the slope is a maximum. That's where that's going to be a peak of the thing. And you could look for the other positions there too. You could also say where this is a peak right here, where the velocity gets to be its maximum. You could also see that acceleration right there is 0. So like as soon as the velocity is getting at its very fastest motion of a changing motion, some motion that's changing with time, we could find out when it's at its maximum, the acceleration is going to be 0, but it's about to change direction, right? So those are important concepts to try to tie together with these derivatives, right? They don't really mean a whole lot until you start seeing them employed as well. Now, we have 3 different cases when it comes to acceleration, right? So acceleration, and this is really where we start with, here's where we start with position, right? We start with position and we get to acceleration. But what if we want to go backwards? What if we know the acceleration for some reason? Someone's given it to us, or through some type of data collection, we're able to get like a function that tells us that it kind of behaves this way. So we want to find out something more about it, right? Well, what we could do is, if we have this right here that we already know, dv dt, right? We want whatever this is a function of. That's the thing we want to use as the derivative onto the thing. So we rewrite this as the acceleration as a function of time. dt is equal to dv. And then what do? We integrate this, right? So hopefully we know the limits that are going on right there. That we know the at time, let's say 0, the velocity is a particular velocity, and then at the time that we care about, it's a particular velocity, right? We know those things, or maybe that's the thing we want to find out. We want to find out what the final velocity is. But this is the idea. This is the big idea that's going on right here. And it could be a little more challenging than maybe what it might seem at the beginning. But now we just integrate this. Now maybe I should have written this over here. We have a as a function of time, integrate of t, let's say t1 to t2. Quite often it's going to be from time 0, right? Because we could just decide this is when we're going to start. So let's make it, this is often going to be 0 right here. And then we're going to take and have the integral of dv, right? Where we're going to have v1 and v. Okay, so let me back up a second. Let me make these. Yeah, I guess I could have left that the way it is. Let me make this, a lot of times we'll say t0, right? And then this will be v0, excuse me. If we integrate, we can't integrate this because this is something that we're going to have to know. But we can integrate this right here as just simply v minus v0, right? Simple. Let's do now the acceleration is a function of position. Now sometimes, don't ask me how that we know that, but we come up with a scenario where we know that its velocity is related to position. And if that's the case right there, this helps us out a lot to have that right there. This kind of like, sometimes I call this the wild card. So if we rewrite that out and we bring that dx over to this side, we say that's equal to, v times dv. Now we can integrate this from, let's say, the original x position to any x position. We can integrate this from the original velocity to the end velocity. Now these things correspond with each other, right? This at this position, that's the velocity. At this position, that's that velocity right there. And we can't do anything yet with this. We need to know what that function is right in there. But if we can do this one over here, right, we could just say it's v squared minus vo squared. Right, so that's this. I like to call this like case 1, case 2. And now here's a third case that we could possibly have right here. Now, the acceleration is a function of velocity. All right, so that's going to be a little weird, but it can happen. And I'll just write it's a function of velocity, right, over on the side. So we have two subcases here, 3.1 and 3.2. Now, if time is the thing that we desire, write out acceleration is a function of velocity dv dt. We always want that d whatever to be on the same side. We want to group the thing up. So you can rewrite this thing as dt is equal to dv over acceleration as a function of v, right there, right? So if we were to integrate this from t0 to t and integrate this from v0 to v right here, we might end up with, yeah, I guess I could just leave it like that. That's the scenario right there. So now if we wanted to find time, we could integrate this right here. But if position was what we desired, right? Acceleration is still a function of this, and we have velocity, and we have dv, and we have over dx right there. What we could just do, rewrite this thing as dx is equal to velocity divided by acceleration as a function of velocity dv, and integrate from x0 to x and from v0 to v. I know, we just messed the thing around, but you get the basic idea, is that we're just trying to get everything lumped over to the side. And here is something that I think is really important to know about in the book, right? So there's very useful things in the book. I try to stick to the book, and there's on Blackboard I've uploaded some resources that are available that come with the book that I think can be helpful. Some videos that they have made for example problems, right? So, but one of the most important things that I think in this book that is going to be helpful to you, that students quite overlook, is this section called Solving Problems on Your Own. And many of the things I've just described will be in this. It's only usually a page long or 2 pages long, and it's always got this green little section, at least in this edition of the book. But you can kind of see this is sort of the thing that you need to know. And then we have the start of the problems that they've included there, and in the back of the book there's the solutions to many, not all of the problems, but many of the problems. So what can really be helpful when you're preparing for an exam, when you really want to try to like own the stuff, I provide a lot of examples and a lot of practice problems, but there's additional ones, right? And so you could just kind of like work through a few of these, not all of them, obviously, but if you really want to own the material, just pick out a problem and, just say, boom, and then work on it till you get an answer. Check the answer, not right, go back and figure out what you did wrong. That, I know it sounds like it's going to be really, really difficult, but it really will push you to make sure that you understand the material. But first do the homework. All right, that, and then you could come to me and ask for help, or you could work through some of these problems, and if you get stuck, you can come to me and during office hours for help. So that's the introduction to the class, to the topic. I'm going to do the examples as separate videos. Some of them are old and or were last spring or maybe a year or two ago that are on Blackboard that I've included. I didn't have one for this main lecture part of the thing, so that's why I'm recording this. Yeah, I think some of the videos looked kind of blurry, so I might have to replace them. So please, if you happen to see the videos, let me know if they're not showing up clearly enough for you. So that's all I had for this part of the lecture. Thank you.